Yes, we're streaming. Just making sure we're going live. Wait. I gotta check. Just make sure everything's doing good. All right. Let me just copy this so that I could do a little bit of what they call jazzy business in the business. Okay. Yes, it's good. It's good. Okay. Welcome to the stream, everybody. It is very zero notice stream as mine usually are. I should probably put notice on my streams if I want to be better at that. But anyway, that's not the point. The point of this little stream thing is to do a little something. Now, there's something in the universe, or not, well, kind of, it's weird. There's something that a human on Earth, something Drake, they came up with something called the Drake equation. Now, some of you might have heard what the Drake equation is if you've ever been interested slightly or remotely with the prospects of astrophysics. You know, it's quite interesting. It's quite interesting. This is the Drake equation right now. I have it on Desmos. It's used to calculate how many civilizations, intelligent civilizations there are that we can contact in the Milky Way, right? Now, it's it just combines a bunch of rates. So I have a good explanation of what the values are on this little image thing that I have right here. So n is the number we're solving for. It's the number of techno. What the fuck did my voice just do? Ignore whatever sound I just made. Oh my god, my computer fans. My computer fans going up. It's like we're taking off. Luna, we're going to Mars. Anyway, number of technologically advanced civilizations in the Milky Way galaxy. So this is the whole the whole point of the thing that we're doing. This is what we want to do. Although we're not solving for the Milky Way galaxy, that's been done for by very smart people. What we want to do is use this for world building purposes, right? So we're going to have this equation be applied to the Migvion galaxy, which is where our star system takes place. By the way, very interesting stuff coming on that. I have 2 episodes planned, and they are no, I don't have 2 episodes planned. I have 1 episode planned. I did have 2 episodes. This is why I record videos so that I could get my editor self to cut out all the weird voice cracks and stutters and ums and uhs that I make, right? But I have shit. Also, I forgot what I was saying. What was it? I said it. Okay, maybe if I just look hard enough at the screen at what I was looking at when I was thinking of it, I'll remember what I was thinking of. N. Oh my god, there's a giant moth on my curtain. I'm not prepared for the stream. Okay, I'll just say something completely different from what I was trying to say originally. What I want to do here is I want to solve for the Drake equation for the Migvion galaxy, right? So we're going to do all that jazz. We're going to have n be solved for, the number of technologically advanced civilizations in the Migvion galaxy. So all these numbers, well, not really all of them, but they're going to be different by little or by a lot. We'll see. Because unlike in real life, this is fiction, and I can decide whatever these numbers mean. Although for some of them, I'm not going to change a whole lot because there's more certain values than there are more whimsical numbers. So I'm just gonna do whatever I want. So anyway, let's get the first value out of the way. R. Now R is defined as the rate or for what. It is the rate of formation of stars in the galaxy. Now, I assume this is going through years because the last variable here, length of time, has to be measured in years. I'm going to keep all the time based things constant. I think there's only 2 variables here. So I don't know if this is number of technologically advanced civilizations per year, but it's or per year squared. I don't even know. We're gonna do a whole bunch of that jazziness. Right, so rate of formation of stars in the galaxy. Now, for our Drake equation, the numbers go between, I think, 3 and 7 or something around that range. I watched a video about it on YouTube, very reliable source of information. But the guy went with 5, and I'm going to also go with 5. You know, Migvion isn't really an incredible galaxy. It's actually smaller than the Milky Way, which itself is kind of small. So it's not really, you know, a grandiose location in the cosmic scale of things. But for a galactic stage, it's just about as good as any other, because at the largest scale, there's going to be so many civilizations, it's going to be unreasonable. But in real life, we think that there's only, I don't know, anywhere between 1 and 20 civilizations that we can come into contact with. The numbers there probably vary a lot, but it's not that many. In my universe, there is a galactic civilization that has set itself up that comprises itself of hundreds of aliens. So we need to get this number up a lot. And it's very hard to do that. So we're going to go with some values that I had thrown away from previous video ideas that I was doing, specifically the ones about other stars. Actually, I don't know if I uploaded that. Oh my god, I think I uploaded that. Did I? Did I not? I don't know if I uploaded it, but we're going to use numbers from a spreadsheet, a different spreadsheet that I had. Not the Conlang retrosector. Was it MISC? That moth is moving around like it's fucking dying. Was it in book? Why is it? It's in. What the fuck? Yeah, yeah. It was in book. Okay. Oh, hey, Luna. She's trying to maneuver herself on pillows. Oh, hi, Luna. Oh, you good girl. She's the best dog. Here, hold on. Okay, that intermission that was very much needed is now over. Ow. I almost slipped in my chair. Okay, let's see. We got the rate of star formation. That is the first variable down. Okay? Now the next variable comes into place. The fraction of those stars with planetary systems. This is how many. Well, that's really obvious. This is actually going to be a higher number than the video that I watched for the Milky Way. They placed their number at 0.9 for 90%. I'm going to go with a much higher number and say 0.96. So FP equals 0.96. So that number is already going to be very close to 5, like immediately. And just know that this is rate of 5 per YR. So, you got that. Now, we're going to go with, I guess we don't have to do, I don't know, it seems dumb. Let's see, that's the wrong tab. We're going to close the tab because it doesn't have the information that I thought it did have. Anyway, next variable on the list, number of planets per solar system with an environment suitable for life. Now, this number is always going to be low because you got planets like gas giants, you got planets like Venus, you got barren planets, you got terrestrial planets, but they're like Mars or they're like a super Earth, to where human life cannot reasonably take up residence. However, I intentionally make it so that I describe as few as possible aliens in the book, because in that universe, while there are hundreds of alien species, there's only so many that they can actually interact with on, an organism to organism basis. So in the early days, interactions with much more exotic life forms were necessary, but now they can sort of distance themselves out into quote unquote groups. It's very relaxed and not xenophobic for how xenophobic it sounds, because it's just really difficult to communicate with a species that you fundamentally don't have a lot in common with. I mean, you got aliens that are comprised of methane, and then you got aliens that are comprised of ammonia, and then you got organisms that are comprised of water like us. And their forms of communication, their sensory organs, all that stuff, it's so different that there's almost nothing that they have in common except that they're in space. So they have to, group themselves into things in order to communicate. And not even all of them decide to group. It's just this section decides the grouping is important. Other sections think that there should be no such thing as grouping. Other sections don't even want anything to do with everybody else. They're just in space for the kick of it. So while the number of planets with an environment suitable for life usually implies Earth, that's probably what the E stands for, if not environment, although it probably does stand for environment. I'm going to go with the literal definition of that, where any planet that is suitable for life, it can exist. And that covers a wide range of planets. That covers a very, very large... Because if you think about it, what kind of planet can't support any type of life? If you get really, really theoretical about it, and you say, okay, take for instance Venus, right? It's literal hell in our solar system. How can Venus support life? Well, there's been theories and a bunch of papers suggesting that there could be some form of microbe in the upper clouds of Venus that have survived from back when it was a much more temperate Earth-like planet. In the distant past, Venus used to be much more like Earth because the star was much cooler and it didn't have its runaway greenhouse effect. But that greenhouse effect kicked off when there was an increase in volcanism and the star got brighter and just a whole nasty combination of things. The spin rate of Venus was really slow. We think it was from some sort of impact with a large planet, but it could have been any number of things, but it probably was a planet. So its spin rate was very, very spun down. And on top of all the other factors, it was just not a very fun deal for Venus. So it had its greenhouse effect, and that increased the atmospheric pressure and the amount of CO2 and the heat of the atmosphere to an insane degree. Now it rains acid, and the pressure is like being under a fuck ton of planes or a shit ton of elephants. And the temperature is like, it's hot enough to melt lead. Everybody says it's hot enough to melt lead. I don't know what that means, but I just know that it's very hot, and I would immediately poof, literally poof, and my bones would melt. So it's very hot on Venus. But people think that in the upper atmospheres, away from all the surface chaos, there's probably water up there. I don't know if we've confirmed that there's water up there. I think we did, but I could be wrong. Look that up if you actually care about me being right or not. But there could be microorganisms surviving from the early days, airborne, in the upper atmosphere. Pretty cool. There could also be subglacial organisms on Mars, although that's much less likely. There could surprisingly, life on Mars is, in my opinion anyway, less likely than life on Venus. You have planets like Europa, or not even planets, but moons like Europa and Titan and Enceladus and fucking, I guess, Ganymede too. I don't know. All these moons, right? All these other worlds out there, Triton, and also Pluto. I mean, it's not really... Okay, the limiters of life are basically boiling down to three things. You have a medium or an origin to create yourself, and then you have to have energy to use and materials to also use. So you have to use the energy to use the materials to cause yourself to live and reproduce. And when you do those things, you're technically considered a living organism, which is why viruses are a gray line, because they don't reproduce on their own. They have to get other organisms to do that for them. But I think viruses are a much, much more archaic version of what life can be on a bare bones basic level, right? Because, I mean, it does kind of expend energy and resources to reproduce. And it does, obviously, it did have an origin. So I guess that first one was really obvious. If life has an origin, it's considered life or whatever. But yeah, this number is much, much higher than what I think a lot of people think it is. I think the video that I watched gave this number 1 in 1,000. But I think that the number of actually habitable planets would be 1 in 10 to 1 to 5. So there's between 1 out of 5 and 1 out of 10. I'm going to go with 12.5%. So number of planets with environments would be 0.125. There we go. Now for the next one. These are going to get increasingly, extremely uncertain. We don't even have one example for this one, but we'll get to that. Fractions of suitable planets on which life actually appears. Now this is much more... okay, so my take on this whole thing is very weird because the video I watched assumed for Earth-like planet. I assume for things like gas giants, where you could have life evolve and appear in the clouds. There's no surface on a gas giant. And you may think, oh, it's really hard for life to appear when there's, like, no actual liquid medium. Well, I don't know. I mean, there could be life at the bottom of a gas giant. Could be. There could be life that forms in large droplets on a gas giant as they fall through a relatively thick atmosphere. I don't know. Life could evolve anywhere in that mess, although it still is very unlikely. Or it could arrive there via panspermia. My voice just cracked again. It's very late at night. It's like almost 1 a.m. But yeah, I'll manage. It could arrive via panspermia, where one planet with life has a small population of that life as microbes or as some other organism. I don't know. Ejected through an asteroid impact. So there's stowaways on the asteroid as it drifts through space, and some life forms on Earth, like tardigrades, some tardigrades, not all tardigrades, but some extremophile tardigrades and other microbes can survive in the vacuum of space for long periods of time. Probably not forever, but they can survive. So it's possible that panspermia can transfer some microbes into a gas giant and they can evolve. Although that's a much more exotic possibility. So it's like mainly us limiting ourselves to the terrestrial planets. But there are a lot of rocky planets orbiting red giants. And, I mean, sure, they're constantly bathed in radiation, but the larger of them should have a magnetic field, and they should be able to deflect a lot of that radiation. So, who's to say, right? Who is to say? There are so many planets that can develop Earth-like planets, or Earth-like planet, Earth-like, not even Earth-like, any kind of life, that it's whatever, right? It's fucking insane. But the fraction of the suitable planets on which life actually appears. Now, this basically rules out all of the gas giants in here. Now, thankfully, I did not include many gas giants, so that brings us down to pretending this were 10%. Right? Because the moth is now flying through the air away from the curtain. So long. Never mind, it went back to the curtain. What moths do what they gotta do, alright? What was I talking about? Oh, yeah. The fraction of suitable planets on which life actually appears. Yes. So yeah, ignoring most of the gas giants, basically all of them, bringing ourselves down to the 10%. The 10% here would be all terrestrial planets. So now considering only terrestrial planets, right? And there could be a bleed over with some gas giants that have life. It could be so. I don't know if they would ever become like intelligent, but that'll probably get canceled out way up here. But the life that actually develops, also very tricky to answer. But for planets that for their chemistry have a lot of it, like Earth is a perfect example of a water world that has the right conditions for water-based organic chemistry. Europa is another good example of that. You could have, okay, think about it. Titan has liquid on its surface. It is as far as Saturn is from the star, from our sun, right? It's frigid cold. Ice on the surface, any water, it turns into ice, and that ice is literally as hard as rock. On Earth, ice is fucking shit. Like, you could hack at it with a pickaxe, it's fine. But on Titan, it is literally what makes the mountains. It's a common element, but like, okay, water is a very common element in the universe. So it's like the rocks on this planet. So I don't know who knows what kind of extreme shit could take place on really hot planets. There could, okay, it's like a scale. I don't know how, I don't know the habitable temperature range of ammonia, but I do know that methane has to be pretty cold in order to be a liquid. So imagine a rogue planet with no star at all, and it has a moon, and it has just enough gravitational energy. Methane based chemistry extends the habitable zone of any form of life all the way to moons of rogue planets or of brown dwarfs. I guess they're not called moons at that point, they could be called planets. To where the tidal stresses of them going around the fucking thing squeeze and stretch the surface, like how Io. I am pretty sure I explained a lot about Io on my channel in the past. Io is a moon where the squeezing and stretching of Jupiter as it goes around its orbit molds the core. It's like rubbing your hands together, friction. It's like Play-Doh. It's being stressed. It's like being massaged by the gravity. And that massaging, that constant kinetic energy being input into the moon, kinetic energy means motion energy or movement energy, that causes it to, have a lot of heat and have a molten interior, which is why it's so volcanic. Now, you can't create energy out of nothing, so this tidal heating is not perfectly stable. But it does last an absurdly long time compared to the lives of stars, unless that star is like a red dwarf. But even then, it lasts a long time. It is not like blazing in all directions either. It's centered. Like, it's a very efficient geothermal energy for the energy input of life is one of the most efficient forms, which is probably why it can last you so long. Take, for example, the most efficient red dwarf stars. They're still shining their energy out in like all these directions. And those last for trillions of years. Now, imagine there was a planet orbiting this red dwarf, right? And imagine if all that energy was concentrated onto the planet. That would be a lot of energy. A 100% release of the star's energy to a planet could be many, many times more powerful. But geothermal energy as like a raw power is much less effective or much less potent than a star is. So while it does have direct efficiency, you need to have a pretty extreme orbit in order to get a good amount of squeeze, But methane chemistry allows for that range to be extended. So not a whole lot of internal stress may be needed for methane inner oceans to act as a molten inners, right? Because all a molten core is a liquid core. Earth has a liquid core. It's like a nickel iron compound. Europa has a molten core, or not a molten core, but a molten interior made of water. One of these methane-based moons or planets around rogue planets or brown dwarfs could have methane-based tidal friction, or not methane-based, but tidal friction that heats methane-based subsurface oceans, and those could house life. And that range from the outermost it can be to like the innermost, to where it like actually becomes, I guess there's no inner limit other than the Roche limit, where the moon is literally destroyed by tidal forces, but the outer limit is extended much further. So it's much more likely that if a planet has methane on it and it can support life, that it will. Because out of this 10%, it's hard to explain this personal opinion I have, but I think that life is. I mean, just look at Earth. Just look at it. The moment the planet cooled down enough for life to form, it formed. Just like that. At the bottom of the ocean, a little doodad started squirming around and all that stuff. I might be exaggerating. It may have not been quote unquote immediate. And it might have not been at the bottom of the ocean, although it probably was. But very, very soon after the Earth became a habitable planet, life formed. And we don't know about other planets. We know that Mars probably doesn't have any life on it. Well, it's going to be very hard to confirm or deny whether Venus has life on it. But Europa I'm a firm believer that Europa has life on it. And not just any life, but complex life at that. I firmly believe that Europa has complex life underneath the ice. I don't know about Titan though, but it's possible, okay? So at the bare minimum, this 10% is going to be put down to 2/3. But I think that it's going to be much higher than that. I think that out of the 10%, it's going to be a 9%. But of course, we're not going to put down 9% because that would be very small. So out of okay, so let's think of it. So we got to get our calculator out. Even though I have Desmos open, I'm just getting this calculator. So 12.5. Hi, please be quiet. Not trying to be rude. Not trying to be rude, but I'm streaming. My mother has returned.
Dun dun
Dun
dun.
dun dun.
The most returning.
The most returning. Shit. 12.5. Okay, so this is the fraction that we have here. Okay, so 72%. That does seem pretty good. So we're going to put the value for, what was it? Fraction. Okay, so f of L. We're going to put f of L at 0.72. Very likely. That's including the gas giants, mind you. If it weren't, then it would be 90%. Yes, now let's move on to the next one. F of I. Fraction of life-bearing planets on which intelligent life emerges. This is also a tricky one because it depends on every instance. It's hard to just whip up an imagine. If we just solve for this equation right now and assume that all the other variables are 1, we get... Oh, really? Half civilization? Oh, that's not... Oh. Okay, she's outside, and I was just thinking about how, like, the sprinklers were on and how that was, like, contributing background noise. But it's fine, it's fine. Anyway, FFI, fraction of intelligent life on planets with life. Again, as I just said, also very hard. Let's crack out our brain noggins and think. My dog's itching herself. Such a simple creature. Now, it tends to be... Okay, we can go under the assumption that if complex life arises on a planet, eventually that life will become intelligent unless it hits setback after setback after setback and never reaches it until the planet is no longer suitable for life, or until all life goes extinct. If Earth has taught us anything, if life can get a foothold, and it does get a foothold, it holds on tight. It holds it by the balls. It does not let go. You throw meteors, you blow up all these volcanoes, you send a fucking quasar at the planet that probably caused the Cambrian extinction or whatever. It probably did. I don't know. all this stuff, it just keeps going. I mean, imagine if the moon crashed into Earth. I'm pretty sure that Chris Gazette made a video about how that's physically not possible. But if the moon crashed into Earth, well, let's be sparing. Let's say at a grazing blow. That's basically saying, like, imagine something just a little bit smaller than Ceres, the largest asteroid, crashing into Earth. Excuse me, I had to do something very important to my dog. I love you. Anyway, it's very hard to cause life to go extinct after it's gotten a foothold. However, this little piece of information here did not say if life ever evolves. So this is basically saying how life will, how long will life survive? Out of the 100%, let's say that okay, let's break this down into parts. Out of our final number, or our pre-final number, we're going to say that, like, after all the, the setbacks and extinctions and stuff, 85% of that life will reach intelligence. Because there could be planets where life just doesn't reach intelligence. But remember, this is my galaxy. I can do whatever I want. I can have any of these numbers be any number that I want. I don't even need to do this. Fuck this. But I'm doing it anyway. So here you go. Yeah, so 85% for our edit to the final number. Now, going back to 100, setting that thing aside, going back to 100 so that we could get to our final number to reduce by 85%, we're going to imagine with our brains that a microbe appears on a planet here, and a planet there, and a planet way over there, and a planet way over there, and all this other stuff. Right? How many of those planets will keep their life for a long time? We basically broke this bit down into 2 bits. How long will life survive, and how sheer luck is needed? Like, how likely is it, just by pure random chance, that a civilization that lives long enough will reach intelligence? So we're trying to figure out how many planets will have life that endures long and prosperous until the planet is no longer suitable for life. And of those planets that have life throughout all their history, we're going to reduce them by down to 85% because some of those perfect planets may not even get life or intelligent life. It may just stay dumb forever. But I find that to be something that isn't super likely to happen, so I'm just going with 85%. So back to the main number again. We're going to assume that most of these planets will not be completely destroyed. Most of these planets with life will not be entirely destroyed. Their environments may change, quite dramatically even, but they themselves will not be destroyed. Although a lot of these planets will be changed beyond recognition with their life on them. So we'll say that 10% of all planets that have life on them will undergo some sort of immense change, or let's say 5%. 5% of these planets will undergo some sort of massive change that completely inhibits life from developing on their surface for a long time, because it'll have to adapt in such extreme ways that it will not be able to keep up with the change, and it's basically a mass extinction that actually works. So 5% of planets that ever have life undergo a mass extinction somewhere in their timeline that legitimately life cannot bounce back from. Now, 5%, for what I said, praising how strong life is quite a lot, but this life is life, right? It could be quite strange. So here, we're gonna make note of this. So down 5% for the first one. Now let's see. we have gotten rid of all the planets who will physically not be able to survive that will go through an intense mass extinction. Now we'll think of all the planets that go through a series of mass extinctions that continuously set back intelligent life until the end of the planet. Now, I'm pretty sure that most planets will constantly develop or will constantly undergo a mass extinction, an ice age, a change in the energy input or output. Actually, I'm pretty sure that's what a mass extinction is. Because, I mean, think about it. Okay, there are two types of extinctions I'm getting here. The first type of extinction is a resource depletion, and the second type of extinction is an energy starvation. A resource depletion would probably be caused by the life itself, like how on Earth there was the evolution of being able to convert carbon dioxide into oxygen. It was called the Great Oxidation Event, or oxygenization event, or whatever. It was a mass extinction because almost none of the life on Earth had the ability to convert oxygen back into CO2. They could only. I'm trying to remember how that event went actually. But anyway, there was a dramatic influence of oxygen into the atmosphere. I think it was photosynthesis or something. But all that oxygen acted against the greenhouse gases and cooled the planet. And not only that, but it was a poisonous gas, so they couldn't really breathe it. So it was a mass extinction event. That was a resource depletion. It was also a depletion of energy. Remember, life only needs resources, energy, and uh, well, they have a planet. Okay, I for some reason my brain is telling me that there's some other third thing, but I can't think of any third thing. So, uh, resources and energy. Those are the materials and energy. Those are the only two things that they need, as far as I'm concerned, right now. Now, material depletion events are caused on the behalf of life. So let's go with the energy depletion events first. So let's see. I'm thinking naturally there's going to be. Well, there's also the third type of mass extinction, which is the disruption, which is actually more common or more stereotypical, I guess, where the environment is shaken up so much that life is set back. But that's only a setback. I don't think that shaking up the petri dish will get rid of all the life. Also, we already covered for that, so no worries, man. Actually, wait a minute. I think I'm being too complicated about this. I think I only need to have an amount of the planets who are constantly bombarded with mass extinctions to the point where they can never develop intelligent life. And mass extinctions are common, but for them to be super common, I think would be quite unlikely. So I'm gonna say, what could we do? I'm thinking somewhere on the side of 10% or lower will be met with a chain of disasters that they cannot compete against. So I think we have a good answer here. Go down by 5, and go down by 10. And then for the last time, what was it, 15? For 15%. 15% will just never reach that point. So let's see. Let's go to yet another tab. Go to our calculator. Let's go to 95. Or wait, let's 0.95 not 98. Let's go to No, 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 no. 0.95 times 0.9 times 0.85. So this would be a 5% increase or decrease, then a 10% decrease, then a 15% decrease. To get 0.7, I'm going to round that to 3 because I'm optimistic. So 0.73. Very, very nice. Okay, now we're getting into fraction of civilizations that develop a technology that releases detectable signs of their existence into space. Now, this is going to actually be quite a big detriment. It's probably going to be the biggest one on this list because out of the civilizations that may be intelligent, not a lot of them will ever have the ability, at least on their own, to leave their planet. For example, Europa, as I mentioned, may not, if they are intelligent or as intelligent as us, they may not have the ability to leave their planet. They might not even know that there's anything out there, but even if they did, they would not know, or they could not break through the miles of ice above them. And then what? They expose their ocean to the vacuum of space, which would basically kill anyone who ventured in there. They maybe have our ambition and like get a bunch of spacesuits, but that's not the point. The point is all of the worlds that have made it thus far that have intelligent life underneath ice oceans are going to be completely discluded from the radio signature thing. Unfortunately. Although this does say detectable signs. So is there any... Wait for it. I love you. Okay. They definitely heard you say that. I heard you say that thrice. I love you too. Weird. Anyway, trying to think. Let's see. They could melt the ice. I don't think they could melt the ice. They could cause some sort of detectable mass extinction, but from that far away through all that. Well, it doesn't have to be quote unquote ice. It could be the solid surface beneath, above them. Let's see. Yeah, I don't think the most effective release of a detectable signature would be radio waves or some other form of um, bleed off of like completely. Radio waves go in all directions and they can last for a while. So, or not a long while, but they can last, and it's the speed of light if you intentionally direct radio signals into space. So, I'm thinking that unfortunately the buddies that live under the ice will not be able to join the party. Very, very sad times. Uh, they might join the party later after expeditions to these worlds decide, hey, what's under all this ice? And then they discover a civilization. But that's not part of our equation. Whatever. That's a dilemma for later me to figure out. Um, so assuming that worlds that are frozen over that have civilizations underneath them account for what percentage of all the planets with civilizations on them? We're going to say that that is... Let's see, I'm erring on the range between 15 and 10%. 50% of all worlds that have intelligent life are under ice? Doesn't seem right. But, I mean, it does seem right, so I'm going to go with 13 and a half. for those that can't release radio waves. Now, for all the others, though, because let's see, other than having a physical barrier above you, what regular planet has the limitation of sending radio waves into space? Well, I mean, there's also the chance that they don't discover radio waves, which is actually quite likely. I realized something very incredible. I can do this. Okay. Now, out of the rest of those planets, the random discovery chance it should be quite high because, well, let's see. If you're an intelligent civilization, as defined by my very biased opinion of what an intelligent civilization is, you have some sort of access to the electromagnetic spectrum and you can communicate with that. We can't see or detect radio waves all that well at all, but that doesn't stop us. Is that a spider? Or is that a fly? I'm pretty sure that's a dead fly. Oh god, it died. Are you kidding me? Whatever. Yeah, this is quite the thinking issue. Let's see, we don't interact with radio waves at all, but we use them to communicate information. Audible information, visual information. We use it to communicate information across distances. And as technology goes on, we're going to reduce that leak, but we can direct radio waves into space. So I guess the main thing here is how many civilizations, and then extra, are aware and want to be found of aliens in the universe and by aliens in the universe. I think the value is not going to be very high. I think it's going to be 70%, maybe 65 or 70. But it's going to be just slightly extra because of the leakage into space, although it doesn't last for a long time. So, it's a small increase. So 0.71. So our number is 0.61415. And now for the last variable of them all, which is the time of civilization. And since this is the last variable, Desmos gives us quite the jolly good show. So how long is this? Length of time such civilizations release detectable signals into space. Oh, okay. Well, I guess we can get rid of the 1 there. And then just add the extra onto this value. So L equals... Good question. What does L equal? Now, these are civilizations that are either at the point where they're having radio wave waste, which means they've reached a technological age, or they are... Here, let's do a very complicated method of this. So we're going to have the numerator, which is the top of the fraction, for all of you who forgot middle school math. We're going to have I don't know what math that was, but we're going to have the numerator be a bunch of different multipliers. So we're going to have the lengths of time for different civilizations. And then we're going to average them all out by the denominator. So for each point, so 1 times 1 times 1, we're going to have this be divided by oh. Wait, hold on. Doesn't make any goddamn sense. What? What? The fuck? Okay, this is really weird. Never mind what idea I had there. We're just gonna multiply together a bunch. I don't even know if that's right. Okay, let's think. At the beginning, we got to take off how many civilizations just die out almost immediately after they're created on the scale of millions of years. So, how many civilizations just kill themselves? Well, that number's gonna. I think that number's gonna be on par with the height of our 70%. Because it's not likely at all. Or I don't know why I said that. It's pretty likely at all that a civilization will kill itself for a variety of reasons. It could be a self-induced apocalypse. It could be that their society is too fragile and there's a minor disruption in that. It could be that they deplete their own resources, like what we're doing. It could be that they kill themselves, also like what we're doing. It could be all these reasons. So at the very beginning, we're going to say that 20% of all civilizations that reach this technological threshold just kill themselves. Actually, we're going to go with 85%. Not on par with our 70% because I guess I was underestimating. Okay. Now, we're going to multiply this. Now, for those civilizations that do not kill themselves off, how long do they last? Oh wait, this is a raw number of length of time. Hmm. It's an interesting equation. Okay, now the stars per year was in years, so our unit of time here is in years. Now, I'm wondering how to represent the math here properly. Now, this is a value that is less than 1 year, so I'm thinking that out of our average, 85% of the people do not live to see that average and will just die pretty much relatively immediately. So we're going to assume that the lifespan of a civilization in the Migvion galaxy, again, assuming that they don't interact with any others, is still quite long. If they reach the point where they do not kill themselves, they will, and they're like sending signals out into space, they're most likely going to be oriented towards space. And they're going to become a spacefaring civilization. And it's not that hard to become a spacefaring civilization once you set foot on your second home planet, because then it's very hard to cause you to go extinct in any way. And when you leave your solar system, it's much, much harder to kill you. So at that point, our number becomes incredibly large. So let's just go with the first example. So 10 to the power of 9 for a million years, and 50% do not see that million year. That bumps up our number. Let's do 1,000 years. Okay, so 100 years. Human civilization has existed for what, 14,000 years? No, yeah, I think 14,000 years. Okay, so yeah, okay. Now, in my lore, the thing has existed for 8,000 years. Okay. Well, that is wait a second. For the 50% takeaway, that's every year. Or no, wait, no, that's out of 8,000 years. 15% go extinct. Which is the exact same thing as saying for every year 15% go extinct. Because everything is multiplied together. All right. So our final number is this. Now, it's very unfortunate that 15% of the civilizations die off as they've become intelligent. Oh. But, what's that? 1,300 become. What? Yeah, I'll just be a second. That was quite the interesting interaction. I love her. But she's kind of strange. Anyway. So let's get all these numbers nice. We're gonna actually change this to 0.6 just to make it nicer. And that does raise it down a little bit. That's 1,300 civilizations. Or at least following the Drake equation. Right? Yeah, over the course of 8,000 years, there will rise 1,300 civilizations. Okay. Okay. All right. Okay. All right. That is the end of the stream. I don't know what to do after that. So our final number is over 1,000 civilizations. That is quite the crowded galaxy. Well, over 8,000 years. Thank you for tuning in the stream. Again, it's a half episode, so it's not like, a real episode. My voice is actually dying. So now is the perfect time to end the stream. Yes, thank you very much. Thank you. An hour long, Jesus. What? Yes. Okay, I gotta get some shit. Goodbye. Your stream will stop immediately, and you. Oh, wait, hold on.